Hey guys, this is 21.8 through 21.12 or 14, wherever the chapter ends. We're really just going to talk about two main concepts and then talk a little bit about problem solving strategies for power transmission. First thing that we need to look at is that when we put current, AC current, through what we call an inductor, okay, sometimes we call them solenoids, but here we're talking about smaller components of a circuit. But anytime we have a loop of wire, it's wrapped around like that, it's going to produce, okay, an effect on the rest of the circuit. You know, this thing has got to remember it's got an AC circuit or AC power source supplied to it, which means the magnetic field will be going this direction, and then it will flip-flop because the direction of the current flip-flops inside of that inductor 60 times a second here in the US. We're in a 60 hertz grid. And so if we're having it switch back and forth, think of it a little bit like momentum. The bigger the current is, the more we're pushing change on that current, the more this magnetic field is going to sort of push back against that change. There will become a lag or a drag as it tries to fight back against those changes as its own momentum wants to continue in the same direction. So that flip-flop is going to cause what we call an inductance or a self-induced current inside the circuit. Essentially what it's going to do is it's going to slow down any changes in voltage or current. So we're going to see that between this point and this point, there's going to be an induced EMF or an induced voltage, okay? And the voltage difference between these two ends around the inductor will equal negative L, which stands for the inductance or the inductance of the inductor, how much it pushes back, times the change in current over the change in time. You know, the more rapidly we change the current, the more this is going to push back or create this voltage to push back against these drops in voltage. Because remember, up here, you know, with an AC circuit, you know, this might be the higher potential initially over here on the left, but then we're going to switch it and it's going to flip-flop 60 times a second. Well, this induced voltage, okay, is going to fight back against that change and try to slow that change from happening as quickly, okay? And so when we want to know how much voltage or EMF is produced, when we want to know how much is produced, we can say that it's the negative inductance, self-inductance, times the change in current over change in time. And this self-inductance is measured in a unit. Ooh, that is not the word unit. In units of henries. Okay, we use a capital H to represent henries. Okay, and that has to do with, again, how much it pushes against that. Now, if I want to know the inductance of a component before I plug it in and try to figure out what voltage there's going to be applied or induced, what we want to do is we want to look at the Mona Lisa equation. I like to call it that. The inductance of the self-inductance of an inductor will equal mu naught, which we know is 4 pi times 10 to the negative 7th, times the number of loops squared, times the cross-sectional area, all divided by L. I call it the Mona Lisa equation because you see the Mona across the top and the length of the solenoid or of the inductor being read from left to right. How long is it? And these are the two equations that we're going to use. They're pretty straightforward to work with. There is a whole nother world of RC circuits and RLC circuits that, you know, given the time and the ability to really dig deeper, we would do a lot there. But we're just, that's not where we're at in this class. We're just trying to introduce some stuff and cover things kind of lightly. That being said, there is one other topic we kind of need to discuss, and that is power transfer through transmission lines and our power losses along the way. What you need to understand is that while the power in and the power out of a transformer, okay, is generally held to be the same, we're not losing a lot of power through our transformer. There's my transformer. Here's my power plant. Okay, the plant. It's going to send power into that transformer, and power is going to come out and run along the power lines. And then down here, there will be another transformer where we step it down, There's probably 2 or 3 substations along the way to get it down to the level I need for my house. Okay? Forgive my bad drawing. I have a very modern house. Okay? All right, so there's my house. I want to get the power to me. The reality is that there is power loss all along the transmission line. While we're going to claim that there's not much power loss, or that the power loss there is negligible in the transformer itself, certainly there's going to be power loss along the way. And depending on how we build our transformer, yes, we will lose some power there, but there's only so much we can do about that. What we can affect is, based on our transformers, we can affect the current that this runs at. Okay? If we can figure out how much current we have running through this line, that can affect the amount of power loss that we're talking about. So a couple of things to keep in mind. Okay, the voltage out of our transformer here is the voltage that we're going to run this line on, and power equals current times voltage. Oftentimes we don't actually know this voltage. We're trying to figure out that voltage, but that also depends highly on our current. So there is another version of this formula that allows us to work pretty cleanly. If we use Ohm's law to replace voltage, then the power along this line is the current squared times the resistance. And here we can see that I squared really emphasizes that the bigger our current is, the more power we're going to lose. So we want to run low current if possible on a power line. High voltage, but low current. So right here, if we look at this equation, if we know how much power loss is acceptable, then if we know how much resistance is in the power line, which in the 2 problems you're doing this, you should know how much resistance is in the power line, and you know how much power loss is acceptable, then you should be able to find the I. And if you know the current, then you should be able to find the voltage during that on that part of the circuit. So understanding that the power loss happens between transformer and transformer along the transmission line. Hopefully this discussion kind of gets you down the right direction. Come in and ask your questions, though, and we'll see you in class. Good luck.